as most people have, I want to thank the organizers. This is a wonderful meeting, a chance to meet people from different communities, and also really nicely organized. So I'm really grateful to have the chance to present this work here. What I'm going to talk is something first on some general terms about quantum classical interactions, then show a different alternative to the methods that have been presented so far, and look at different applications or different examples that have to do with symmetries, with uncertainties, entanglement, and things like that. So let me start with some general reflections. Okay, I forgot I have an outline here. I will, after the general reflections, I will talk about hybrid systems, the approach of ensembles on configuration space. This is this alternative approach that I want to present. And then I'll look at symmetries like Galilean invariance. I'll look at the interaction of two quantum systems via classical mediator. That has been a topic of discussion in the last couple of years regarding entanglement and the need to quantize gravity. I also put in something about uncertainty, which I may or may not skip, and then some conclusions. So what is a hybrid or a mixed classical quantum system? Here's a pictorial representation of it. If you think of classical mechanics as being the king on the ground, as being a lion, and quantum mechanics being also masterful in its own realm, the air. If you want to build a hybrid system, you basically put the two of them together and have a graphon, which is what I'm showing in the bottom. And well, we all know that graphons are fantastic animals. This fantastic has two meanings. It could either mean that it's something that surprises you and that makes you very happy. But fantastic also means that it doesn't exist in real life. And I will leave it ambiguous which of the two meanings one should take here. The thing to notice is that you can't just combine these two animals to create the graphon in an arbitrary way. If you put an eagle's head and a lion's head and no feet, nobody would recognize it as an animal. If you put just one wing and one claw from the eagle, it would also not work. And for the hybrid systems that we are dealing with, we have similar situation. And the main issue, I would say, well, the two main issues are we need to find a common mathematical ground. And we also need to deal with some conceptual issues. And this is a reflection of this point I was making, that you can't just create a fantastic animal by putting bits from this animal and bits from the other animals. It has to form another animal at the end. So we need to keep some things from quantum, some things from classical mechanics, but it's not clear what it is that we need to keep. And as a matter of fact, one of the big obstacles in the field, I think, at least as far as the communication between different approaches, is that classicality means something different in each of these theories. And we have many, many variations on a theme. I don't think this is necessarily negative. On the other, I think that this variety of approaches stimulates a lot of work. And we see that in this meeting, that there's a lot of crosstalk. But one has to be aware that there are many approaches to it. We've also seen some of the motivation for doing this type of work. We've seen some remarkable practical applications of applying hybrid systems to very complicated systems. And in my opinion, this is something that gets a green light, in the sense that this is something that it's really something we want to do. There's also, I would say, what I will call work in progress. And this is what has been brought to the forefront time and time again in this meeting. There's no full theory of quantum gravity, and the alternative of combining quantized matter fields with a classical gravitational field is very attractive. And I would point out it has there's two reasons why it's attractive. One is to see if there is a consistent way of doing this coupling. But the other one is to see how the different theories might fail. Because if you remember, before quantum mechanics, we had the old quantum mechanics, which is a mixture of classical concepts and quantum concepts. And there was as much value in seeing what worked in the old quantum theory as there was in seeing what failed, because it's when you run into obstacles that you have to change things. So I see this as these two aspects as being complementary and being useful. Where I think one needs a little bit of caution is applying hybrid systems to foundations of physics. There is definitely a lot of insight that is gained from it. And you're pushing both classical and quantum systems to the limit in some sense, and you're learning about them. But there's also a tendency in the field to get a result in within one hybrid theory and assume that's a universal result. And I think one has to be a bit wary about this. And this is not just now that this system has become more formal, but also in a number of older thought experiments, like the one that Jonathan mentioned about Feynman, for example. So my concern in this talk is a bit more towards applying this to foundations of physics, and I want to show you some examples where you do get different predictions with different models. What I also want to do is present this other alternative, which we've called ensembles and configuration space. This is work that has been done in collaboration with Michael Hall. As a matter of fact, everything that's in this talk is pretty much work that we've done together, except for things that I quote from other people's papers. But because it's a different approach, I would like you to forget for a moment what you know about hybrid systems and just listen to how this one is built. And then later there will be a chance to compare to other systems. It starts from a very simple idea. Basically that ensembles of physical systems are at a very basic level. When they are subject to uncertainty, and I'll assume that there is uncertainty for any description that we give of a physical system, you can describe them by terms of a probability density on the configuration space. So you have a certain configuration that's available to the system, and some states will have different probabilities. And what we want to do is we want to set these probabilities in motion, because we want dynamics. And what we will do here, we will assume that this dynamics can be ruled by an action principle. And for convenience, and also because a lot of the physics becomes clearer, we will assume that it's a Hamiltonian formalism. So what we will have is what I call an ensemble Hamiltonian, to distinguish it from the usual Hamiltonians that we encounter in quantum mechanics and in the phase space of classical mechanics. This is a functional of P and S, and it's solely put in there so that we can have some dynamics of the probabilities. So the state of the system at a given time will be described by P and S, and the equations of motion are Hamiltonian. Keep in mind also that up to here, there's no physics. I mean, this could be a probability distribution that has something to do with biology, with psychology, with economics. It doesn't matter. This is a very general framework. And the other thing to keep in mind that there are no, if you're thinking in terms of particles, there are no trajectories in this approach up to now. So when it gets to particles, you can complete the theory by adding trajectories, but at the moment it's just dynamics of probabilities. This is sort of a basic, then very primitive, if you may, description just in terms of statistics. Now, to get to some physics, what we need to do is define the dynamics first. And what you can do is describe here, for example, a pair of non-relativistic particles. You can describe their motion by introducing this ensemble Hamiltonian, which, if you look at it, is just the energy as determined by a Hamilton-Jacobi equation, and you're taking the average of it. And if you look at the Hamiltonian equation of motions, when you look at the time derivative of S, you get the Hamilton-Jacobi equation. And if you do the other variation, then you get a continuity equation for the probability. So essentially what you have here is basically a probability on configuration space that moves according to the vector field defined by this function S. And this is what I will call a classical system. It's a slight generalization in that you're allowing for some uncertainty in the positions, but basically you're doing Hamilton-Jacobi theory. And by now you will probably guess that you can go to quantum mechanics, or perhaps is a bit surprising, but all you need to do to go to a quantum theory is add a term to the Hamiltonian, to the ensemble Hamiltonian, and then you get equations of motions that are basically the Madelung equation of the motions, or quantum mechanics in the Madelung formulation. And you can do a transformation, you can define a wave function, and then just go to the Schrödinger theory. Now, I want to emphasize that I'm not trying to do any reconstruction of quantum theory or any reconstruction of classical theory. I'm just bringing both of them into a common mathematical framework. One thing that is useful is that this Madelung transformation is a canonical transformation. So since we're doing Hamiltonian mechanics where the phase space is the function P and the function S, then everything that we do here, we can either do in this hydrodynamical variables of Madelung, which have a more of a intuitive classical meaning, or we can do it in terms of wave functions. And if you go to a wave function representation, you will have what in Wolfgang Schleik's talk was called the classical matter waves, which obey a nonlinear equation. And this formulation of quantum mechanics is essentially the formulation that George Broglie referred to in his talk. I mean, the one that Kibble formulated, where he uses a Kähler geometry and he uses a Hamiltonian formalism. And this is an approach that George Broglie has expanded a lot and applied to other methods and really developed. But this mainly remains here. I mean, one can take this theory and give it a geometrical framework. I won't do that here. And if you do it and you restrict to a quantum to the quantum case, then you have essentially Kibble's theory. So there's nothing particularly new about these reformulations of classical and quantum mechanics, but what is new is that now you have both theories in a common framework, and then you can hope to build a hybrid theory. Originally, this was developed not to look at hybrid theories, but to look at some issues that have to do with Fisher information theory, and deriving quantum mechanics in a new way. But at a later point, Michael Hall recognized that it could be used for these hybrid theories. The crucial aspect here, oh no, sorry, I'm getting ahead of myself. So how do you define an ensemble Hamiltonian for a mixed theory? Well, you simply sum the two Hamiltonians, the quantum and the classical one, and add an interaction term, which is typically what is done in all of these type of theories. And here the interaction term, I will assume it depends only on the coordinates. And then what you get are equations of motion that are no longer linearized by a transformation to a wave function. And this is an important difference with other theories. This is a nonlinear theory. The same way that the classical mechanics is nonlinear, this hybrid theory is nonlinear, and one has to be careful then with the behavior of the theory. But you get a continuity equation that is, thank you, Lajos, that is well behaved, and you can prove surprisingly a number of consistency requirements like positivity, conservation of energy. The oscillator comes out nicely, and so on and so forth. I have a couple of transparency for later, somebody asked, but it has very nice consistency conditions. And in the heart of the theory, I would say, is this transparency here. It turns out that you don't only have the Hamiltonian or the correct equations of motions, but what this map allows you to do is actually map the whole Lie algebra of classical observables that you get in the usual phase space of particles to an algebra of Poisson brackets, but now it's a Poisson bracket that refer to the functions p and s. So there are two different spaces, the function of x and p's of your classical particles, and this space here, which is a space of two functions p and s. And you get an isomorphism between the classical phase space algebra and the algebra in this space, provided your observables are defined in this way that's shown on the left side. That is, if you have a function of x and p in this new space, you just define it as a function of x and the gradient of s. A similar thing holds for the quantum theory, and this is not surprising given the equivalence with formulation of Kibble. If you have a quantum operator, you can define a functional of p and s using this equation, and you can show that this Poisson algebra in this new space is isomorphic to the algebra of commutators of the quantum operators. And you see that the observables look very different. So if you have a classical particle and a quantum particle that you make, you have them interact, they have their own different types of observables. And this, even in the case of a hybrid system, this preserves then an idea of what is classical and what is quantum. And I noticed in the talk by Raymond Caprell, he was mentioning that it was unfortunate that there was a lack of a Lie algebra structure in the hybrid system that he was using. This is not a problem here. You have a Lie algebra structure, and it reduces to the usual Poisson brackets of particles in the case of a classical system, and it reduces to the commutator algebra in the case of a quantum system. So you're carrying a lot of you're carrying all of the algebraic structure of each of these theories into this common space. And one thing I will mention because of the interest
side is the C supposed to be a Q?
Which C?
The extreme lower right of your slide.
Yes, thank you for pointing that out. That is a typo. Yeah. No, that is not a typo. I correct myself. That's bad notation. What I'm trying to say here, yeah, that should be a Q. You're right. Thank you. Yeah, it's not bad notation, it's a mistake. So just a few words on application to gravity. This approach, this formalism, can also be extended to fields. And you can look at a classical gravitation field interacting with quantized matter. And to get there, you basically have to extend this formalism from particles to fields, where before you had the Hamilton-Jacobi equation for particles, now you have to use the Einstein-Hamilton-Jacobi equation. And for the quantum sector, you typically have to then use the functional Schrödinger equation in this other variables. This is not particularly nice because solving the Einstein-Hamilton-Jacobi equation is not easy. And also the functional Schrödinger formulation is in some senses not as developed as the other formulations of quantum field theory in curved spacetime. But the advantage is that it does remain close to Wheeler-DeWitt equation. And there are ways of solving the Wheeler-DeWitt equation in a perturbative way, and some of these techniques can be borrowed here. But as you can imagine, we haven't done too many calculations about that. We have some calculations in a book that we published with Michael. One of them, you can take a classical CGHS black hole, that's a two-dimensional black hole, sort of a toy model, and join it to a quantum scalar field. And if you do a perturbative solution at one of the lower levels of perturbation, the second one, I think, you get quantum field theory of curved space-time. So this is nice that you recover that. That's a general thing that you get also for other theories of gravity. And this means that you can also look at Hawking radiation, everything you can do of quantum field theory of curved space-time. The higher orders become much complicated, and we haven't looked at that. And you can look at cosmological models, for example, and there's some special solutions that you can solve. But it hasn't been really, it has been formulated, there's some calculations, but not much. But I wanted to mention this due to the interest in gravity. So are there any questions up to here? Because now I'm going to move on to applications. Okay, so let me move on to a couple of applications. I mentioned that there are differences between different hybrid systems, and one of the things that I've been interested in is representing symmetry groups. And one thing I want to show here is how this works, for example, for the Galilean group, if you have a two non-relativistic particles, rather, if you have a hybrid system and you want to look at the Galilean group. So I won't go into the details of the Galilean group. I think everybody's familiar with it. It has 10 generators and it satisfies a given Lie algebra where the mass appears as the central charge. And to look at the symmetry here, what you need to do is look at the observables of the theory, because the observables of the theory are these expectation values, and you represent or you map the Lie algebras of either quantum or classical particles to this algebra of observables. And this is straightforward to do. The generator of translators is essentially the momenta as it appears here. You always here have an average value. Rotation has a similar expression. For the Galilean transformations, you can also take it directly from what we know of representing boosts in quantum mechanics or classical mechanics. A thing about notation, I have two sets of coordinates. The Q coordinate, I assume, is the coordinate of the quantum particle, and the X coordinate is the coordinate of the classical particle. And S and P are going to be functions of all the coordinates, both quantum and classical. And for the generator of time translations, then you assume that you have the sum of the observables for the energy for the quantum and classical particles, and you allow for an interaction term, which here I assume is just depends on the coordinates. And if you plug all this into the Lie algebra, then what you get is that you need to have a potential that depends on the relative distance between the quantum and classical particles. This is identical in a purely classical or purely quantum case. The central charge is just the sum of the masses, and you get trivially momentum conservation because your generator of time space translations is also your total momentum observable. So you immediately reproduce what you get for either purely classical or purely quantum system. I was interested in seeing how this looks in, for example, the formulation of Sudarshan, and I only found one paper about this. And I have to admit that I don't know that much about it, and it might be that there are other ways of doing this, but I'm going to refer to this recent paper from 2020, where this is worked out in some detail. And you take the same algebra, but Lie algebra, but now you want to use operators that are acting in the hybrid Hilbert space. And there what happens is that you get similar expressions. Here I've showing them in a different order, but you can define your generator of time translations, space translations is the momenta, rotations is what you expect. The Galilean boosts, you can also write them down. This is using the prescription on how to write the classical generators in the Sudarshan approach, and is also using the fact that there are some operators in which are not observables, as is well known, but they need to be there for in the generators. And what happens was a bit surprising to me. You now look at this interaction term that you allow in the Hamiltonian, and look at the Lie algebra. And what is reported in this paper from 2020 is that you have some conditions. If you require that you have a classical acceleration observable, if you introduce that, then it turns out this puts some constraints on the interaction term. It has to be independent of lambda x and can be at most linear in lambda p. If you then put this into the algebra of the Galilean Lie algebra, then you get further restrictions on the dependence of the interaction on the possible terms. But then when you look at conservation of total momentum, then it really restricts the interaction term to the point that you cannot allow for interaction terms that are relative, that depend on the relative distance of the quantum and classical particles if you want momentum conservation. And this is because there's an additional constraint that comes from the fact that the generator is not necessarily, or is not the same as the observable, because we have this multiplicity of operators and some of them are not observables. And the generators typically use this non-observable generators. But this has then some serious consequences if you're doing foundations of physics and you want to define a non-relativistic hybrid system in terms of the Galilean Lie algebra, because it restricts your interaction to the point that you cannot, for example, have a harmonic oscillator that depends on the distance of the quantum and classical particle, or a gravitational field, or things like that. My point here is that one has to keep in mind that these hybrids, that the conclusions that you get are always model dependent, or almost always, or in general are model dependent. And if you're using then such a hybrid system to make statements, general statements about properties of classical quantum systems that have to do with foundations of physics, they need to be qualified. And I think this is an interesting case also given the new developments in the Sudarshan type of formulations Sari has done and co-workers, because it would be interesting to see if such symmetries can be introduced in a different way. That is, if there are other formulations, or there might be already, I just restricted to the original Sudarshan approach. It might be interesting to see if the new formulations can find other ways of implementing not just Galilean invariance, but other invariance terms. Yeah, that's the other thing that's where there's a strong difference here is the fact that while in some of the formulations of hybrid systems, like the one that I presented, the observables and the generators are identical. In others, you have to have this doubling, and the observables are not generators, and this can create some ambiguities, I think. The other case I want to look at is consider two quantum systems that interact solely via a so-called classical mediator. And Michael and myself, we wrote a paper on it about 2 years ago, a bit longer than that, commenting upon a couple of papers that made the claim that one cannot get entanglement between two quantum systems if they solely interact through a classical system. And this is, again, as far as I understand it, something that is to some extent, is model dependent. That is, it depends on the properties of your hybrid model, and in particular how you define classicality. And I want to show you the calculation first with the model that I presented to you, and show you that you get entanglement. And then a mean field theory type of model where it's clear, it's very easy to see that no entanglement is produced by such a setup. So first, I need to be clear what I mean by entanglement in this model, because it's not a Hilbert space model and it's not very intuitive. But what I will take for entanglement is a very, say, primitive, basic view of it, which is that if the wave functions factorize, there is no entanglement, and otherwise you have what I will call entanglement. This is the definition that goes back to Schrödinger, whose original paper. It's clearly not entanglement in the sense of Bell, because there the entanglement means that you cannot introduce hidden variables that are local. But it turns out that in this theory that I showed you, if you want to add hidden variables for a classical system, you can do it. They're just trajectories of the Hamilton-Jacobi equation. And then you can show that you don't have any non-local hidden variables, which is what you expect in classical mechanics. So you can complete the theory, and you can show that you don't have entanglement in the sense of Bell. But I will, as I say, use this more primitive notion that goes back to Schrödinger. What we have done here is we've looked at a simple coupling between classical and quantum particles. So Q and Q prime are the coordinates of the quantum particle, and X is the coordinate of the classical particles. And we have an interaction that couples the momentum of Q to the position of C and the position of Q prime to the momentum of C. We are looking at an approximation that is common in measurement theory, where you assume a sudden interaction. So any kinetic energy terms of that would be in the Hamiltonian, you can ignore for a short period of time when these particles interact. And this is done here because one can also show that there is no superluminal, there's no action at a distance with such an interaction. The theory that I have here is a theory that under certain conditions, under certain interactions, can have action at a distance. And for the theory to make sense, you have to introduce some assumptions about classicality, about the size of what it means for an object to be classical. But I can go into that at a later point. At the moment, I just want to point out that there is no action of a distance here. And I can show you how this comes up also. So what you need to do here then is essentially solve the Hamiltonian equations of motion. They are the ones that I show here in the top line. They're quite simple because it's a simple type of coupling. And they're first order differential equations. So there's an arbitrary function there, and you can write them out in the way that I've written them. And you can you see what happens is that the position X gets there's displacement of the positions, but there's also a quadratic term. So Q gets displaced. Let me just go back quickly here. As I said before, the momentum of Q is coupled to the position of C, and the momentum of Q prime to the momentum of C. Because of the coupling of the position of Q prime to the momentum of C, then, sorry, is this, yeah, Q to the position of C, then Q gets translated depending on this coupling constant G1, and the same thing with the position X, because it couples to the momentum of Q prime. But there's also a quadratic term that comes out of these equations. And you can write this in terms of a hybrid wave function by using the Madelung transformation. And the point is that if you start with ensembles that are initially independent, that is, if you have a hybrid wave function that factorizes, and you turn on the interaction for a given amount of time, then what you end up is with a wave function a hybrid wave function that no longer factorizes. And if you imagine that these particles have moved away and are now very far away, and you you measure, for example, the position of the classical particle, then you end up with a reduced wave function in the space of the two quantum particles, which doesn't factorize. So this indicates that you can cause entanglement through an interaction with the classical system in this formulation, and that the statement that this would be a proof, that no entanglement would be a proof that you don't have a classical interaction, is certainly not supported by this formulation of hybrid systems. It just doesn't hold here. So there's a loophole for this statement. If you look at mean field models, and a mean field model is a model where the classical system is represented by phase coordinates. We've seen these models in the conference, and you have a quantum a wave function for the quantum sector. And then you have dynamics, which is a Schrödinger equation for the wave function and Hamiltonian equations for x and p. If you have this mean field model, then you don't create entanglement. You can show that you can assume that your interaction factors in this way. This is the assumption that the two quantum particles don't interact directly, but only through the classical mediator. And then if you look at the evolution, you get an evolution that doesn't create entanglement. So this theorem or this statement or this claim that you cannot create entanglement through a classical interaction is valid, but only on a certain class of models, not every hybrid model. And I've added a transparency here, which I won't go into this in detail, but this I just added it a little while ago. This connects to what Jonathan was presenting earlier. You can also model the measurement of spin, and you introduce a coupling term, which is just the product of the momentum of the classical system, the SDX, multiplying the spin variable, which is alpha, which can be either plus or minus, and the ensemble Hamiltonian is just the average value of this coupling. And it's very simple to solve the equations of motion. And the point that I want to make, if you look at the last slide, if the probability of spin up is W plus and the probability of spin down is W minus, then this uncertainty gets propagated to the pointer. And what you end up here then is an equation that tells you that with probability W plus, you will see the pointer move to the right. And with probability W minus, you will see the pointer move to the left. So this satisfies this condition that Jonathan was presenting of diffusion, or I would formulate it here in terms of propagation of uncertainty. And this is also a big difference with other hybrid systems. Here we assume that both classical and quantum systems can be subject to uncertainty. And we mean this in the sense of that if a system interacts with an uncertain system, then you don't really know with certainty what happened to the system that interacted with it. Yeah, I'm out of time, so I just want to end here with a couple of statements. I'm of the opinion that such systems should be used to formulate and answer questions in foundations of physics, and this is something that interests me the most. But there's also a warning, there's a yellow light that one has to evaluate to what extent these conclusions apply universally, or they're just the result of a particular hybrid model. And I think this is something that gets forgotten in the arguments about quantizing gravity, because not always, but sometimes arguments are made which implicitly assume a particular type of coupling between classical gravity and quantum fields. And then conclusions are reached that are not universal, and one has to be aware of that. And I think that I will end with that, and I'm happy to take questions.
Right, thank you very much. Thanks a lot. This was very well presented, and I particularly appreciated the honesty. The first question is from Jonathan, and then I would like to get back to your question. Jonathan, please.
Thanks for a great talk. I wasn't sure if the last concluding remarks and some of the remarks, were they whether they were taking aim at what I was saying or not, in the sense that, well, I don't mean in a, I mean in
No,
a
I know what you mean,
way,
yeah.
but because it seems to me that, you know, the statements such as that you are required to have decoherence and you are required to have this diffusion, that seems to be model independence. And so I was wondering if you were taking aim at that or not.
So as I was reading this concluding remark, and of course I wrote them before I heard your talk, I was about to say, but this doesn't apply to what Jonathan said. And then I thought it was a bit awkward to single you out, though it would have been more honest. I think that the statements that you made in your talk, and I said during your talk that I agreed with statements. I think without having looked at it into detail and having looked at all the calculations, I have the impression that they are generally valid, and it's something that also it's the impression that I had also when I looked at the example of Feynman, for example, and also the other example of Epley and Hanna, which we discuss in a paper with Klaus Kiefer, and other examples, that in many cases this dispersion or this transfer of uncertainty to the classical sector is not taken into consideration. And I also believe this is a universal issue. And also I think decoherence is something I haven't really thought much about, but now after your talk, it brings to mind to look into that. What I was criticizing is something different, which is statements, even if with the insight that you brought about the Feynman example, that it neglects diffusion. This type of statements, of course, this is a statement made in the 1950s when there was just the beginning of all of this, and there wasn't so much thought about many of these things. But even in the statements of Feynman, he uses the statement that the gravitational field has to have an amplitude. This is how he formulates it, and he gets questioned back and forth by the other participants in the meeting, and he never gives a mathematical response. And at some point, he says he's just figuring it out. So I think there's a lot of these things were not thought out to a deeper extent.
Okay, before I leave the word to Professor Dioshin and else, I would like to get back, since you asked the question to me and you presented the material in a certain way. So I would like to address your question. So the question whether these hybrids are Galilean covariant or not, this is a perfectly good question. We did not look into the details. However, you did show that the original Sudarshan hybrids do not possess momentum conservation. I don't know if you remember reading our paper, but we did show in our paper that our variant does have conservation of total momentum. And this is a particular consequence of translation invariance of the interaction potential in that case. So it's not a full answer, but we have indications. Yeah.
Okay, no, I apologize for that. That is clearly something that I overlooked when I originally looked at the papers and didn't go back to when I was preparing the talk. But it's good to hear that, and good to know that there's not an issue with a more modern or the new approach that you're following. Okay, Professor Diossi, please.
Yeah, Marcel, you showed us that the fact if a classical mediator can or cannot create entanglement is model dependent. So just allow me the judgment that if in a given model a classical mediator can create entanglement, then in my decent judgment, this mediator is not sufficiently classical. So I mean that I'm sure that if there is any reasonable model that is hybrid, then the classical part cannot create entanglement between two quantized systems, because then the classical part does not possess the eminent features that we must assume for a classical system.
Yeah, this is a point well taken. One of the I guess I was alluding to the fact that one of the big difficulties is understanding what classicality means. And for example, are you to allow dispersion of the classical sector, or you allow uncertainty in the classical sector? Which type of interactions do you allow? In this case, we have a type of interaction that models that it's, let's say not models, but it's close to what you would find in a quantum system, for example. And these are valid critiques, and one has to then, in the light of this, revise to what extent one is willing to extend the definition of classicality. I would argue that it is these calculations and these efforts that allow you to refine what you believe is classical or not, and to distinguish between which theories you are you willing to keep or not. And in this case, I take it as a valid criticism to say it's not classical enough, and this model has to be either rejected or modified. I, of course, have a different view on it, but it requires more calculations from my side.
Professor Els.
You hear me? Seems loud. Hi, Marcel. Nice talk. My question goes basically in the same direction what Lajos was asking. And you remember, I mean, a long time ago, we had a lot of discussions about our different approaches to this hybrid description of hybrid systems, in particular about the various consistency requirements which both theories fulfill. But there was one crucial difference, namely, and I think you published it even yourself with a collaborator, that your approach tends to produce spurious correlations where there should be none. And my question is, has this been resolved, first of all? And secondly, is this somehow reflected in your possibility to create entanglement? Because in my theory, you don't create entanglement, and we studied the coupling of two qubits via a classical oscillator, and there is no entanglement whatsoever. Thank you.
Yeah, so we were extremely careful when we published the paper on the entanglement to choose interactions that we can prove don't have this property of memory or action of a distance or things like that. So these particular examples, and we have more than one example in the paper, and since then we've looked at others, don't suffer this problem. Regarding whether the problem has been solved or not, it depends. It's something to be discussed, and this has to do with classicality. I show you from the paper that I published with Michael, showing that this is a real effect in the theory. If you have a classical observable that just depends on its position, it turns out that you can have, when you look at the acceleration, a small contribution from one of these four Poisson brackets. And here I show an example that's been worked out in the case where you have kinetic energy terms and things like that. And it shows you here what type of, that indeed you have this case. And we looked at it also numerically and confirmed that this happens. Now, there's one thing that one can argue. It probably take too much time to go to the details now, and we can talk about it. But one thing, if you, as you saw in the example of the spin, once you do the measure of spin, you have a pointer that has a certain probability to point in one direction or in the other. This is the outcome. And when we think about the pointer or any classical device, it has to be a stable, heavy, big device. And it's something that doesn't exist in a vacuum, but there's an environment that is surrounding it. So there will be a process which is akin to the coherence that you get from the environment in quantum mechanics, just by the interaction of all the photons floating around, or if you turn on the light to read the indication. So one further constraint that has to be made to this theory is to say, well, if you have a classical system, it really is a classical system. It's big and heavy, and it's not, these superpositions are not they're not superposition, but these double peak structures are not gonna be there for a long time. They're actually gonna disappear almost immediately. And then you're gonna get the systems after the interaction has ceased are gonna factor again. And once the systems are independent, then there is no possibility of action at a distance. So it's not quite a fix in the sense that this effect is there, but it's a bit like the argument from decoherence that there's a reason why you don't see certain quantum superpositions at the macroscopic level because of the action of the environment. Okay. As I say, there's not enough time to discuss it in detail, but this is the main idea, and this is presented in a couple of sections in our book, where we present the problem and then argue for this type of solution.